So a nice application of calculus is to that of arc length, to compute the length of curves in the plane and also in space. So we're going to be able to compute lengths using integrals and using calculus on functions, of vector-valued functions. So how do we compute the length of a curve? You can see that if I have a curve here in blue, then I can approximate its length by doing a polygonal approximation of that curve. And the sum of those lengths of those segments would be the length of the curve, or an approximation of. And then you can see, just use the same idea in calculus that we've used over and over and over again, which is now make those intervals. I've cut my curve into several intervals in time. As I travel this in time, just divide that interval into sub-intervals, and then make those intervals shrink. And what we're doing is really doing a limit of a sum, so it is a Riemann integral of lengths. What happens to one of these lengths as the subinterval, the length of the subinterval goes to 0, is that I get the tangent vector. I get the tangent vector at a point. So at the end of the day, when I do a limit to compute this length, I'm doing an integral over the lengths of tangent vectors. Okay? And we know how to compute a tangent vector. You've seen, I think you have seen already in calculus 2, perhaps, what is the arc length for a curve in the plane is given by a formula like this. And then you can see that if you want to compute the length of the tangent vector at a point, remember that we had, if this was given by RT, then R prime of t, if this is given by a function of x, a function for the y, and a function for the z value in terms of t, then R prime is the derivative of x prime, the derivative of y prime, the derivative of z prime, all with respect to t. And then the length of that vector would be the square root of x prime squared plus y prime squared plus z prime squared, which is precisely what I have here. So this integral for arc length is just integrating the lengths of tangent vectors from one place to the other on the curve. Between time A and time B, whatever you have traveled, whatever piece of the curve you've traveled from time A to time B. So in both dimensions, in 2 dimensions and 3 dimensions or higher dimensions, arc lengths are measured by an integral of the lengths of the derivative of your vector-valued function. And as we have seen, if the vector-valued function is 2-dimensional, the derivative is given by this inside the absolute value here. And then the length of that vector is this square root, which is the formula you probably learned in calculus 2 for the arc length of a curve on the plane. And if you're doing a vector-valued function in space, then the length of the tangent vector is given by the square root of the squares of the derivatives of each coordinate. And when you integrate that, you get the arc length of a curve. So let's see an example. In the previous lecture, we saw this example a bunch of times, where I had this curve in particular starts here, and then it just like spirals up in the z direction. And they're asking me to figure out what is the length of essentially a full rotation. Yeah. Oh, I think I know what you mean. What you are looking at is you're thinking of a function that is of one variable, and you're computing the length of the curve, right? So I have here A, here B, and you want to compute this length, the length of this piece of a curve. Then I can write that as a vector-valued function in 2 dimensions, as this would be R of t that would be, the x would be just t, and then the y, so if this was y equals f of x, then the y is f of t. Okay? So in that particular case where your graph, where the line that you want to compute a length of is the graph of a function in one dimension, then r prime will be the derivative of t is 1, and the derivative of f is df dt. And then compute the length of that. So I would go from a to b a square root of 1 squared plus df dt squared dt, which is what you said it was correctly, 1 plus the square root, or the square root of 1 plus the derivative of the function. But so this formula is more general because it's for vector valued functions which are not necessarily the graph of a function. So these ones can be more complicated without being graphs, and I can still compute lengths of those without being the graph of a function in one variable. So you can simplify that formula to a graph of a function of one variable, and then you get the one that you mentioned. Okay? Okay, so back to this example. We are going to compute this length. I need to know at what times I hit one point and at what time I hit the other one. So you can see that at time 0, I am at cosine of 0 is 1, sine of 0 is 0, and t of 0 is 0. And then if this point is on this path, I know what t actually has to be. I figure out that it has to be time 0 because the third coordinate is just t. So time 0, I'm at this point. At time 2 pi, I'm at this point. So at time 2 pi, I'm at the point 1, 0, 2 pi. I have to compute the derivative. R prime of t is minus sine t cosine t 1. And I have to compute the length of my derivative vector. That will be the square root of the square of the coordinates of the derivative. So minus sine t squared plus cosine t squared plus 1 squared. And sine squared plus cosine squared is 1. So it turns out that this is a square root of 2. So the length of the derivative vector is not constant at all, because we can see that here is like this, and like this, and like this, and like this. By the way, the points that I'm integrating from are now from here all the way up to here. Okay, so I'm doing the length of one full loop of this spiral, of this helix. And the length of the tangent vector is always a square root of 2. So now the length that I'm looking for will be, I know now that I have to go from time 0 to time 2 pi. And then I have to integrate the length of the derivative vector. So it is the length from 0 to 2 pi. It turns out this one is just very easy because the length of the tangent vector is constant, a square root of 2. So that integral is just 2 square root of 2 pi. You just apply the formula and you get the result. So let me do one more example of arc length. Now they tell me the times to integrate. I don't know exactly what this looks like. All 3 coordinates are growing, so this is probably escaping somewhere in the first octant, some curve that is growing, but just escaping to infinity, all in the first octant, when x, y, and z are all positive. So I don't think it's a very exciting curve to begin with, but we can find the length of this curve. I need to find what is the derivative vector. The derivative will be 2t, and 3t squared divided by 2, so t squared. I have to find the length of this vector. So let me do that also here separately before I go into the integral sign. This will be the square root of 2 squared plus 2t squared plus t squared squared. And that is the square root of 4 plus 4t squared plus t to the 4. Is that a perfect square inside the square root that is going to help me simplify this? Is this a perfect square? It's t squared plus 2. So this is the square root of t squared plus 2 squared, and therefore it is just t squared plus 2. So now the length that they're asking me to do, to compute, is from time 0 to time 1, length of the tangent vector dt, and that is the integral from 0 to 1 of t squared plus 2 dt, which is t cubed over 3 plus 2t between 0 and 1, which is a third plus 2, which is 7/3. And that's it. Of course, these integrals, because it's the integral of a square root, can get pretty complicated fairly soon. So these two that I just did work out very nicely, but some of these integrals can be definitely complicated. If you pick a curve in space at random, this integral is going to be fairly tricky to solve explicitly. But of course, you can always use some numerical method to approximate this number.